morning. I welcome you all to this session of fluid mechanics. Today we will be continuing the discussion on ideal fluids, the ideal fluids part 2. Now last class, if you recall, we discussed about the stream functions and the velocity potential functions and the streamlines and the velocity potential lines, equipotential lines for source and sink flow. If you recall that, now we can see here that a source flow is a flow which in a two-dimensional plane can be thought of as a line source, which is seen end on as a point where from the fluid is coming out uniformly in all radial location. This is a source, and sink is the reverse of this, where the fluid is approaching towards a point uniformly from all radial directions. All right. So in this kind of flow, we derived earlier the stream function was given by m, where m is the strength of the source, which is the mass flow rate, total mass flow rate coming out from this source, by twice pi rho into theta with a minus sign, and the velocity potential function was recognized as m by twice pi rho ln r by r0. All right. So where this r0, so therefore first of all let us see that the constant psi lines, that is the stream lines, is psi is equal to constant where theta is constant, that means the radial lines. So radial lines are the stream lines. Similarly, equipotential lines are the lines where r is constant if you make phi is equal to constant. So these are concentric circles. And r0 implies a radius where we have considered an arbitrary value of 0 for the phi function. Now for a sink, this is for a source. So for a sink, the stream function for sink is just with a negative sign, because source and sink are physically same, only with a negative sign. Similarly, phi for a sink will be, that velocity potential function for a sink will be like this. Now today we will see the superimposition of certain basic flows. Now superimposition, let me write superimposition of basic flows, superimposition of basic flows. Now one thing you must know, that when two flow fields are superimposed, if the velocity vector of one flow field is v1 and the velocity vector of another flow field is v2, that means v1 and v2 are the velocity field of the two flows which are superimposed with one another, then the velocity vector, the resultant velocity of the flow field will be the vector addition of these two velocity vectors. Since psi is a linear function of the velocity vector, then if psi1 represents the stream function for one flow and psi2 for another flow, then the resulting flow will have a psi function or a stream function of, or the stream function of the resulting flow will be the sum of the stream functions of two flows. This is because stream function is a first order derivative of, not first order, rather I will tell first power, bears a first power relationship with the velocities, because it is simply the derivative of the velocities, velocity gradient. So therefore the basic conclusion is that if psi1 is the stream function for one flow and psi2 is the stream function for other flow, if these two flows are superimposed, the resultant flow psi function can be obtained by the addition of the psi functions of these two. Now with this method, with this basis, we can now see first the combination of source and sink. Source and sink, combination of source and sink. Now let us consider a flow where a sink, source and sink located like that. Let A is the source and B is the sink. A is the source, B is the sink. Now if we consider a point P in the flow field which is generated by the combination of source and sink, now we can write like this, that if we just join these 2 points, let this is theta 1, theta 2. In a polar coordinate system, we can write that for source, this psi, that is psi 1, that is psi A, is minus m by 2 pi rho, all right, theta 1. Now for the sink at B, psi B is equal to negative of that, so therefore it will be twice pi rho theta 2. So therefore, we see the psi function for the resulting flow, that is the flow which results in due to the combination of the source and sink, will be psi A plus psi B, which can be written as m by 2 pi rho into theta 2 minus theta 1. All right. So this theta 2 minus theta 1 from geometry is this angle. So therefore, we see psi is equal to theta, where theta is the angle APB, where theta is angle APB. Now here we see one interesting thing, that the constant psi function lines, that means streamlines, are those lines along which theta is constant, because if we put psi is equal to constant, which will give theta is constant, which means these will be the circular arcs, that means the streamlines will be the circular arcs with AB as the base chord, so that this angle will always remain constant. That means this will be the this will be the, for example, this is one circle whose chord is AB. So this is source, this is sink, so this will be the streamlines. So other circular arcs can be thought of these streamlines like this. Now we can develop the expression for stream function in a Cartesian coordinate system. Let us consider this x, let us consider the y axis. Let the coordinate of any point is xy. Then therefore we can write tan, this theta 1 and theta 2 is there. Now we can write tan theta 1 is what? Y, the y coordinate of the point, divided by b plus x, where we take this distance as b. That means the coordinate of A, where the source is kept, is minus b0, and the coordinate of B on the positive x axis, where the sink is kept, is b0, which means if this be the origin, OA is equal to b, OB is equal to b, so b plus x. Similarly, tan theta 2 is equal to, theta 2 is this angle, we drop a perpendicular from the point P on the axis, we will get y is into x plus b. I am sorry, x minus b. X, this is x minus b. It is x plus b, it is x minus b. All right. So therefore, we can write tan theta 1 minus theta 2, which is equal to, you know the formula for this, tan theta 1 minus tan theta 2 divided by 1 plus tan theta 1 tan theta 2. So therefore, we can write tan theta 1 minus theta 2 is equal to, if you replace this, y x plus b minus y x minus b divided by 1 plus y x plus b into y x minus b. So if you simplify it, it will come 2by divided by x square plus y square minus b square. So therefore, we can write with this that the psi, okay, here we can write, therefore psi is m by 2 pi rho theta 2 minus theta 1. So, well, it is theta 2, I am sorry, we will have to make it theta 2 minus theta 1. So theta 2 is x plus b. So theta 2 is x plus, theta 2 is x minus b, it is x plus b. So this is all right. So it has to be theta 2 minus theta 1. I am sorry, theta 2 minus. So if you see that theta 2 minus theta 1 is tan inverse this, that means tan inverse x square plus y square minus b square. So therefore, in Cartesian coordinate, we get the stream function psi is equal to m by 2 pi rho tan inverse in terms of the Cartesian coordinates 2by x square plus y square minus b square, where 2b is the distance between the source and the sink, m is the strength of both the source and the sink. Now we will consider a case where source and sink are placed such a way that the distance between them tends to 0 with the condition that the strength times the distance remains finite or constant. That means the source and strength are kept at a distance and ultimately they are approaching towards each other, the distance between them tending to 0 with the constraining equation that the product of the strength and the distance of separation is constant. So this type, the flow field which is arrived is known as doublet or dipole. The flow field which is arrived by this way, combining source and sink in this way, is known as a dipole. So what we can do, this is the combined stream function for a combination of source and sink. From here we can see that if 2b tends to 0, that means this tends to 0. So tan inverse of a quantity which is tending to 0 can be written as the quantity itself, which means that tan inverse x at x tending to 0 is equal to x itself. So therefore we can write under that limiting conditions for a doublet or dipole, psi is equal to m by 2 pi rho with this mathematics into 2by divided by x square plus y square minus b square. So limit of this as b tends to 0. Now when b tends to 0, but bm is constant, so that we can write bm by pi rho, cancelling this 2, bm by pi rho into y b tending to 0, that means y by x square plus y square. Or simply we can write in terms of polar coordinate bm by pi rho into r sin theta divided by r square. Considering these as a constant c, we defined a constant c as bm by pi rho because bm is constant according to the definition of this type of problem. So therefore we can write c sin theta divided by r. This is the stream function of a dipole. So dipole will be like that. When you see this source and sink will approach each other, this angle will become 0, and ultimately these circular arcs with AB as the base chord will become tangent, will become circles with tangent at the x axis at the origin. That means this will be the nature of the this will be the nature of this now, okay, this will be the nature of this dipole, where dipole is at the origin because they are placed symmetrically up from the origin and they are tending to the distance of separation tending to 0. This is the dipole or doublet, streamlines of the dipole or doublet, constant stream functions. Now we will come to a very interesting phenomena or very interesting situation by superimposition of rectilinear flow, which we have discussed earlier, rectilinear flow and doublet Now the superimposition of these two flow gives the stream function for the resultant flow, which is the sum of the stream functions for rectilinear flow and that of doublet. Rectilinear flow, if you recall, the stream function is given by uy, where u is the velocity of the rectilinear flow, but here rectilinear flow parallel to x axis. So it is the superimposition of a rectilinear flow parallel to x axis and the doublet. That means here if we see that there is a rectilinear flow parallel to x axis, if you take this as x, this as y, this is u. So stream function for this rectilinear flow uy we have already discussed, and this is the stream function for the doublet. So if you superimpose a rectilinear flow with the doublet, then what you get, uy plus c as defined earlier for the doublet sin theta by r. Now if I write y in terms of r and theta in polar coordinate system, so it will be r sin theta plus c sin theta by r. This is the typical stream function for the combination of rectilinear flow parallel to x axis and the doublet. Now you see that in this type of stream functions we get some interesting thing, that at psi is equal to 0, that means if we consider one value of the stream function arbitrarily to 0, that means along a streamline where psi is equal to 0, we get some conclusion that sin theta is either 0 degree or 180 degree. That means if sin theta is equal to 0 and 180, the value of stream function is 0. We can ascribe the value of stream function to be 0. Another solution is that for any theta we can get a value of psi 0 provided UR is equal to C by R, or simply R square is C by U, or R is equal to root over C by U. Let this root over C by U be denoted by A. That means for all values of theta, psi is equal to 0 is obtained along points whose radial coordinate R or radius vector R is constant, because C is a constant for the doublet and U is the constant because rectilinear flow, the velocity U is constant, which is parallel to the x-axis. So this is constant. So if you replace now mathematically root over C by U is equal to A, then we get psi is equal to minus U sin theta into R minus A square by R, because C is A square U, minus U sin theta R minus A square by R. So this is the streamline which is obtained. Now if you write this streamline again, that psi is equal to minus U sin theta into R minus A square by R. This is the streamline which is obtained if a cylinder is placed at the origin. That means this is the axis x, this is the, in an infinite expanse of a parallel flow of an ideal fluid. That means other way we can tell, if a parallel flow in an infinite expanse of an ideal fluid, a cylinder is placed, the way the streamline will be deflected by the cylinder will be given by the similar functions. That means these psi functions, that means if we make this is equal to constant, the locus given by this theta and r coordinates will be similar to the case when an parallel flow parallel to this x-axis for an ideal fluid will be deflected by a cylinder which is placed at the origin, whose axis is at the origin. That means it is the ideal flow past a circular cylinder. So therefore, the stream functions or streamlines for an ideal parallel flow past a cylinder like this can be generated by the combination of a doublet and a rectilinear flow. Let us find out two velocity component. One is the tangential velocity component. That means we define, for example, this is the direction. So with this direction we define this is theta is equal to 0. Now another very interesting thing is that psi is equal to 0 is along the line theta is equal to 0, and this is theta is equal to 180 degree or pi. And for all theta, this is the surface of the cylinder where radius is constant. So A here in this equation will represent the radius of the cylinder. So this is the stream function for a parallel flow of ideal fluids past a circular cylinder whose radius is A. So therefore, this line, that means the fluid particle following this line theta is equal to 0 along the cylinder and then going via this line, and another is diverted in this way, this corresponds to psi is equal to 0. These are the lines corresponding to other values of psi. Let us find out the v theta and Vr at any point here or any point here. What is the definition of tangential velocity in terms of the stream function? If you recollect, this is del psi del r. That means this becomes is equal to minus u sin theta, if you differentiate it, 1 plus a square by r square. Similarly, if we find out the radial velocity, which is connected with the stream function as 1 by r del psi del theta, and with a negative sign. This is positive, this is negative. So this becomes is equal to u cos theta into 1 minus a square by r. Now at the surface of the cylinder, r is equal to a. So at r is equal to a, we clearly see Vr is equal to 0, which is obvious. At a solid surface, there cannot be any radial velocity of the fluid, because solid surface is impervious to the fluid flow of fluid until and unless it is a porous surface. So the solid surface, there cannot be any component normal to the surface. This is one of the very important and universal boundary conditions, that for an ideal flow, in viscid flow, there cannot be, even for an a real fluid, there cannot be any normal component of flow velocity on a solid surface until and unless the solid surface is porous. So therefore this is 0. Whereas V theta at r is equal to a, we get, if you put it there, we get minus 2u sine. So there is a tangential velocity. So no slip condition will not prevail here because the fluid is ideal, there is no viscosity. So fluid slips or flows past the cylinder in a direction, surface of the cylinder in a direction along the surface. So it is minus 2u sine theta. Now from here one thing is very clear. So this function is symmetrical. This function is symmetrical about this axis. That means the velocity over this zone from 0 to 180 is same as 180 to 360. But it is not symmetrical about this axis. If you think this, the velocity first becomes 0 here, theta is equal to 0, then it goes on increasing at theta is equal to pi by 2 because the sine function attains its maximum value there, and then again it is reducing from pi by 2 to 180, and the same trend continues in this arc with a negative sign. That means the numerical value of the velocity is 0 here and then increases to the maximum, again comes to the 0, and same thing is repeated here. So therefore velocity field is symmetric about this axis. Now at these 2 points, theta is equal to 0 and theta is equal to 180 degree, these 2 points the velocities are 0, and these 2 points are known as S, stagnation point. As you know, we have discussed earlier, where the velocity, when a particle approaching along this line theta is equal to 0 strikes this surface and its velocity is totally destroyed, means it is converted only into the pressure energy because there is no other destruction. That means the kinetic energy cannot be converted into intermolecular energy because fluid is frictionless. So velocity is converted into pressure, and there the fluid particle is at rest. Similarly, the fluid particle is at rest. It reaches the maximum velocity here. These 2 points are known as stagnation points, where in a flow field, stagnation points are those points where the flow velocities become 0. These are the points at theta is equal to 0 and theta is equal to 180 degree. This is known as forward stagnation point, and this point is known as a rear stagnation point. Now if we look the pressure field, what happens? Now if we describe the pressure at the far upstream or far downstream as the undisturbed pressure known as free stream pressure P infinity, then we can write the Bernoulli's equation at any point in the far stream at any point near the cylinder where the flow field is developed due to this cylinder in this fashion according to the stream functions or these velocity functions, the velocity expressions of the velocity. Then we can write P infinity plus, here the velocity field is only u, plus half u square is equal to pressure. That means we are interested to find out the pressure at any point, the pressure distribution equations, P plus half velocity square. But now if we take the point, any point at the cylinder surface, then what will be the velocity at the cylinder surface? The radial velocity is 0. So the only velocity is the v theta. So this is the velocity at the cylinder surface, minus 2u sine theta whole square. Okay, so we can write P is equal to P star plus half u square minus, this is 4, this is 2. So therefore this will be becoming minus half twice u, this is 4 twice u square sine square theta. Now this is the pressure distribution equation. Now we make it in a non-dimensional fashion, express P minus P infinity, the difference of pressure at the surface from this far stream pressure divided by half rho u square as 1 minus, well, 4 half rho u square 4 sine square theta. So this is the pressure distribution equation. So now if we write this pressure distribution equation again, we see that the pressure distribution equation becomes P minus P infinity in terms of this dimensionless quantity. This is the dynamic head based on the free stream velocity. This is the difference between the pressure at any point and the free stream pressure. This is known as Cp, pressure coefficient. This is known as pressure coefficient. This becomes 1 minus 4 sine square theta. Now if we plot this thing, you will get a curve like this. If we plot this thing, we see, we better plot here, we will get a curve like this. Now here if we see that from theta is equal to 0, this is theta, this is 0. At theta is equal to 0, this is 1. That means P minus P infinity half, that means P is P infinity plus, that means this is the stagnation pressure. Here if you see here the V is 0, that means this velocity is 0. So pressure here is stagnation pressure. That means the dynamic head based for this free stream parallel flow is converted into pressure. So this is the stagnation pressure. So Cp is 1 here. So then pressure goes on decreasing as the velocity goes on increasing. I have shown you earlier the velocity increases over this part. So therefore pressure continuously goes on decreasing. And you see this function reaches, if this is Cp in this direction, this is the theta, this function reaches a minimum value at theta is equal to pi by 2, which is 1 minus 4 minus 3. So therefore we see this reaches a minimum value at pi by, so this is left minus 3 and this is pi by 2 or 90 degree. Then again it goes up and takes the value of 1, again this is 1, the same value when theta is 180 degree. So this function you see is symmetrical about this axis, but the variation takes place, it is not symmetrical about this axis. So we show only the variation from 0 to 180 degree. So it shows that it is, just if I draw this thing again, the streamlines are like this, streamlines are like this. So therefore this is the streamlines, so this is the streamlines, so this is the streamlines, so this is the axis. So therefore you see that this pressure distribution over this line from 0 degree to 180 degree, that means these two stagnation points, this goes on decreasing. So this part the fluid is accelerating and pressure is decreasing. So this is the maximum velocity and minimum pressure point. So this is Cp, the pressure coefficient. Again this part the fluid is retarding, velocity is decreased because we have seen earlier the velocity function, then the fluid pressure is increased and it recovers the same pressure. There is no dissipation of pressure into intermolecular energy because fluid friction is absent. So this part is the accelerating flow, this part is the retarding flow. This can be well understood that if we consider a surface here a certain distance away from the cylinder, you will see that for flow in this part, this gives a convergent duct. So curvature is such as if it is flowing through a convergent duct, whereas flow in this part, the curvature is such it is flowing through a divergent duct and the pressure is therefore increased and velocity is decreased. Now one important thing comes that if we consider the force, net force acting on the cylinder, so it is an ideal fluid. So cylinder surface, the only force acting is the pressure force. This is the pressure force. Only force acting is the pressure force because there is no force along the tangent to the cylinder at its surface because there is no viscous force. So this is the only force P. Now if we want to evaluate the force acting on the cylinder along x and y direction, x is the direction, that is the direction of the flow, the axis, flow axis, parallel flow, and y is the transverse direction, the direction perpendicular to this parallel flow direction. Then we can write Fx is equal to, if we take a small element here at an angle theta of radius, this radius is a and this subtended angle is d theta, the radius is a. So we can write the force on this element is P, if the pressure is P, so the a d theta, this is the length of this arc, a d theta, per unit length of the cylinder in this direction, that is in a direction perpendicular to this plane of paper. So per unit length, this is the force on this element, P a theta. So if you take its component cos theta will be its component in this x direction because this is the angle theta. So therefore cos theta, if you integrate it over the entire cylinder, you will get. Similarly, Fy will be, if y is taken positive upwards, minus 0 to 2 pi P a d theta sin theta. That means simply we can write Fx is P a cos theta d theta integrated over 0 to 2 pi and Fy is integration of P A sine theta d theta, integration of 0 to 2 pi. Now this you see, if the pressure involves a function like this, then if we multiply, this is an even function of theta sine theta, so this is independent of the sine theta. So therefore the pressure variation is symmetric about this axis. Now if we multiply this function with cos theta and sine theta, and if you integrate to 0 to 2 pi in both the cases, you will get 0. That means in this case what happens is that the entire cylinder does not experience any force in x and y direction, which means the pressure distribution is symmetrical over the entire cylinder, so that it gives neither a force in x or y direction, because here you see the sine p minus p infinity by half rho square is independent of the sine theta, so that it is almost symmetrical. That means it is symmetrical about both this and this axis. So therefore no force is exerted in either x or y directions. So all right, next we will discuss a combination of rectilinear flow. We will discuss the combination of rectilinear flow, the same flow parallel to y axis, x axis, plus doublet plus a irrotational vortex, plus an irrotational vortex. You have already seen, let us first before that discuss a little bit of irrotational vortex. We have already seen that an irrotational vortex flow, that a vortex flow which is irrotational, the tangential velocity is described by some constant by r, c by r. Let this constant be denoted by c1 by r, because we are already handling with one constant c in the stream function of doublet. And Vr is 0, that means vortex flows are the flows whose streamlines are concentric circles. That means it has got only tangential velocity, where the velocity bears a functional relationship with the radius like this, c1 by r, radial coordinate, and there is no radial velocity. This we have already seen. And for this type of vortex flow, the rotation is 0. That means omega is 0. The rotation component is 0. Omega z is 0. That means the vorticity in r theta plane is 0, that we have already recognized. So this flow is known as irrotational vortex flow. So the irrotational vortex flow, if you want to derive the stream function, how can you derive the stream function? You can write v theta is del psi del r and Vr is minus 1 by r del psi del theta. Since Vr is 0 by the definition of any vortex flow, so psi is not a function of r. So psi is a function of r only. That means we can write d psi dr instead of del psi del r, and v theta can be written as some constant by r. So if you integrate it, you get psi is equal to c1 ln r by r0. So r0 is a constant, comes after the integration, which physically signifies that at r is equal to r0, psi is equal to 0. That means we define an arbitrary value of psi is equal to 0 at r is equal to r0. And also you know that a free vortex motion can never be described up to the center or the origin of the coordinate system where r is 0, because here v theta is undefined, infinite. That gives a point of singularity. Now if you recall the definition of circulation, gamma, we know this is defined as the closed contour integral of v dot ds, where ds is the elemental. ds is a vector if you take along the element, along an elemental length along a path, and closed contour integral along a closed contour, and v is the velocity vector. So in a free vortex flow, in that way, if we define if we evaluate the circulation, we will get that ds means, let the radius is r at over any circular path, and this is d theta, so this ds is r d theta, and v dot ds, v is only in the tangential direction v theta, so v theta r d theta, and v theta is c1 by r. That means it will be 0 to 2 pi. Along the closed contour it will be 0 to 2 pi. So c1 by r cancels, so it is c1, and d theta is 2 pi into 2 pi. So therefore 2 pi c1. Therefore this constant in the velocity function defining the tangential velocity in a vortex flow is nothing but gamma by 2 pi. So therefore, the V theta can be written, usually written in terms of the circulation constant like this, and psi also can be written as gamma by 2 pi. So because C1 is gamma by 2 pi, this we have put ln R by R0. So if we know now this thing, now the combination of the rectilinear flow parallel to x-axis, doublet and irrotational flow gives a stream function which is, first of all, the rectilinear flow and doublet gives the stream function which already we have derived as minus u sin theta into r minus a square by r. Only with this we add gamma by 2 pi ln r by r0. Now here we will notice always that when we add a circulation term or an irrotational flow vortex, irrotational vortex motion or a free vortex motion, then what we get? We get an asymmetricity because a separate additional function is added with it. Let us see now if we just try to find out the V theta is del psi del r. Let us see what is V theta, that is del psi del r. That means minus u sin theta 1 plus a square by r square. If you differentiate this, we get gamma by again twice pi r. And if you write Vr, it will be minus 1 by r del psi del theta. That means u cos theta, same thing, r 1 by r del psi del theta. That means it is 1 minus a square by r. And this part will be 0. This is independent of theta. So therefore, on the surface of the cylinder, that means mathematically at r is equal to a, that means if we plot the cylinder here, on the surface of the cylinder r is equal to a, Vr is 0. But what is V theta? V theta Vr at r is equal to a as usual 0. But V theta at r is equal to a doesn't give only minus 2u sin theta in this case, because this first term will give the similar term, the same term minus 2u sin theta, but added with another term twice pi a. Alright, so minus 2u sin theta plus gamma by twice pi a. So therefore it is distinct that this term creates an asymmetricity. That means velocity vector now is not symmetric about this axis, about this x-axis. This is because sin theta changes its sign from 0 to 180 degree and 0. So 0 to 180 degree sin theta has got one sign, and the sign of sin theta changes from 180 degree to 0. So therefore this sign is changing, and this is superimposed with a constant term gamma by 2 pi a. So therefore V theta is never symmetric about this axis. So that means the flow field becomes asymmetric. That means the flow field about this half and flow field about this half will be different. Okay. Now let us find out then the stagnation point. Where at the stagnation point? Where V theta is 0? Where at the stagnation point? That means if V theta is 0, if we put here, we get sin theta. Then we don't get theta is equal to 0. Then we get sin theta is equal to gamma by 4 pi a u. Now there may appear now gamma, then we get sin theta is equal to here, if we keep it here. So there may appear three conditions. When gamma 4 pi a u less than 1, it may appear gamma by 4 pi a u is equal to 1, and there may case gamma by 4 pi a u greater than 1. Now it is less than 1, that means it will occur on the cylinder surface, because sin theta is defined for less than 1, and it will be displaced up. That means in that case, this is the case when gamma by 4 pi u less than 1. So the streamlines will be like this. So this will be the stagnation point. So this will be the streamlines. So these are the stagnation points. These are the stagnation points. This is gamma by 4 pi a u less than 1. When gamma by 4 pi a u is 1, that means gamma by 4 pi a u is equal to 1, then this streamlines is like this. Then the stagnation point just merges here at pi by 2 line here, x and y. So this will be the streamlines. This will be the direction of the streamlines. So this is the stagnation. But gamma by 4 pi AU greater than 1 gives an impossible case for sin theta, which means physically that the stagnation point is never occurred, or never occurs on the cylindrical surface. That means in that case there is no stagnation point in the cylinder surface. The flow velocity is like this, and the stagnation point in that case, this is the stagnation point. In that case, this will be the streamlines pattern. So this is the case when gamma by 4, 3 situations are there, greater than 1. So stagnation point will not occur on the cylindrical surface. This is the case gamma by 4 pi u is equal to 1 and gamma by 4 pi a less than 1. Sorry, this is the case when this is less than 1. Sorry, this is the less than 1. So 3 distinct cases are there, the pattern of streamlines depending upon the values of gamma by 4 pi a u is less than 1, that is stagnation points on the cylindrical surface, it is lifted up, then it is equal to 1, it is at this point, and it is greater than 1 in this source. Stagnation point will not be occurring on the cylindrical surface. So today, okay, I have to end here. So next time I will just complete another part, that the velocity distributions and the pressure distribution for this type of flow. That is the combination of rectilinear flow, the doublet and the irrotational vortex. Okay.